Right now, beneath the quiet countryside near Geneva, a 27-kilometer ring of superconducting magnets is slowing down. The hum that once shook the foundations of modern physics is fading. And you weren't supposed to notice. For over a decade, the European Organization for Nuclear Research, known simply as CERN, has been firing protons around that underground circle at 99.99991%, the speed of light, smashing them together, recreating conditions that haven't existed since a fraction of a second after the Big Bang. That machine, the Large Hadron Collider, gave us the Higgs boson. It confirmed the final missing piece of the Standard Model. It proved that empty space isn't empty at all. And now because it failed. Not because it broke, but because what comes next is far more ambitious. You're living at the edge of a transition in human knowledge, a moment where physics might either crack open the universe or admit it doesn't understand reality at all. And the new plan? Much deeper. When the Large Hadron Collider first switched on in 2008, it felt like humanity had built a cathedral to the invisible. 27 kilometers of tunnel, buried beneath France and Switzerland. Magnets cooled to 1.9 Kelvin colder than deep space. Protons guided through vacuum so pure it rivals interplanetary emptiness. If you could stand inside the tunnel while it ran, which you cannot, you wouldn't hear explosions, you'd hear precision, a tight, disciplined hum, like the universe clearing its throat. Then in 2012 it happened, a ripple in the data, a statistical bump. A particle consistent with the Higgs boson predicted in the 1960s by theorists including Peter Higgs. When CERN announced the discovery, physics didn't erupt. It exhaled. It was the mechanism that gives particles mass. Without it, atoms would not form. The LHC confirmed it. The Standard Model, humanity's blueprint of fundamental particles, was complete. And that was the problem. Because when scientists looked closer, something was wrong. The Standard Model works with astonishing precision. It predicts experimental outcomes to absurd decimal places. But it explains only about 5% of the universe. The other 95%? No, it says nothing about gravity at quantum scales. Nothing about why the Higgs mass is so unnaturally light. Nothing about why matter exists at all instead of annihilating into radiation after the Big Bang. It's like solving a jigsaw puzzle and realizing the picture on the box was a lie. So CERN pushed harder, increased luminosity. More collisions, more data. They searched for supersymmetry hypothetical partner particles. Nothing. Results sharpened the tension. Physics was no longer about discovery. It was about doubt. If the LHC couldn't reveal cracks in the Standard Model, maybe the cracks weren't where we expected. And that's when the proposal emerged. Not an upgrade, a replacement. Imagine a collider not 27 kilometers long, but 91 kilometers in circumference. A machine so vast it would carve a new ring beneath the Earth around Geneva. A structure 3 times larger than the LHC. This is the future circular collider. Its goal isn't just to smash particles. It's to measure the Higgs boson with unprecedented precision. To test its interactions so finely that even tiny deviations could reveal hidden physics, new forces, new particles, maybe entirely new layers of reality. Instead of searching for spectacular new phenomena, it will hunt subtle anomalies, slight tremors in the equations. Because sometimes revolutions don't explode, they whisper. The new plan is insane not because it's reckless, but because of its scale. Estimated cost, tens of billions of dollars. Timeline, decades. Energy reach, up to 100 teraelectron volts, nearly 8 times the LHC's design energy. But energy isn't the only frontier. There's another proposal more radical. Linear colliders stretching tens of kilometers in straight lines. Electron-positron collisions instead of proton collisions, offering cleaner signals. Precision over brute force, because smashing protons is messy. They're composite particles made of quarks and ugly ones. Collisions are like colliding Swiss watches made of smaller gears. Electrons are simpler. Cleaner collisions mean cleaner truths. And then there's an even stranger idea. Muon colliders. Muons are like heavy electrons. They decay quickly in microseconds, but if you accelerate them fast enough, relativity stretches their lifetime. Time dilation becomes an engineering tool. Imagine building a machine that relies on Einstein's time dilation to function. That's not science fiction. That's the drawing board. Because the Higgs boson may be the doorway. Its mass is about 125 GeV, bizarrely small compared to the Planck scale where gravity becomes quantum. Theoretically, quantum corrections should push its mass enormously higher, unless something stabilizes it, something unseen, maybe supersymmetric partners. Maybe compositeness, the Higgs, isn't fundamental but made of smaller pieces. Maybe our understanding of spacetime is incomplete. If the Higgs field fluctuated slightly differently, the universe would be uninhabitable. Atoms unstable, chemistry impossible. We are balanced on a razor's edge, and the LHC may have only scratched the surface. But here's the tension. What if there is no new physics at reachable energies? What if the standard model is simply correct up to scales we can never experimentally probe? That possibility terrifies physicists more than failure, because it would mean we are trapped. Limited not by intelligence, but of. You can't just double energy forever. Engineering constraints grow monstrous. Superconducting magnets demand insane cooling, infrastructure costs balloon. Societies question the value. The future circular collider would be one of the most expensive scientific instruments in history. So when people say they're turning off the LHC, they imagine retreat, but it's not retreat. It's a pivot. The LHC will finish its high luminosity phase later this decade. It will continue collecting data. But the frontier is shifting, physics is entering its precision era. And precision can be more disruptive than power. Because if the Higgs deviates even slightly from predictions, even 1%, the entire theoretical landscape shifts. A small crack can shatter a cathedral, but the implications go beyond particles. Dark matter remains invisible. We infer it through gravitational pull on galaxies. Through structure formation. The LHC has not produced dark matter candidates.
What if dark matter doesn't interact through weak-scale physics? What if it belongs to an entirely separate sector, a shadow universe coupled only through gravity?
Colliders might never see it, and that possibility is forcing a philosophical shift. For a century, physics advanced by building bigger accelerators. Higher energy meant deeper insight. But now we face a fork in the road, bigger machines, or different questions. Itself. Telescopes are becoming particle detectors. Gravitational wave observatories detect black hole mergers. Cosmic surveys map billions of galaxies. Maybe the answers lie not underground, but overhead. Still, CERN new plan refuses to surrender the accelerator paradigm. Because controlled experiments matter. In space, you observe what the universe gives you. In a collider, you decide what collides. Those following Earth, those fears are misplaced but of irrelevance. What if after spending decades and billions, the future circular collider confirms the standard model again? No new particles. Just confirmation. That would be revolutionary in its own way. It would tell us that the universe is simpler or more distant than we imagined. And that realization could redefine physics. Because maybe the next revolution isn't about smaller particles. Maybe it's about information. Spacetime as emergent geometry. Some theorists suggest spacetime itself is not fundamental, that it emerges from quantum information networks. That gravity arises from entropic principles. If that's true, smashing particles might not reveal the code. We might need new mathematics entirely. So when they turn off the Large Hadron Collider, it's not an ending, it's an admission. We reach the edge of a paradigm. Now we must decide how to cross it. And as the hum of superconducting magnets quiets beneath Geneva, humanity stands in a strange position. We have mapped the particles of existence. We have equations of breathtaking elegance. And yet, we don't know what 95% of reality is. The next machine, whether circular, linear, or muonic, is not just an instrument. It's a gamble, a bet that nature still has secrets within our reach. Because if it doesn't, if the universe's deeper layers lie forever beyond experimental access, then physics transforms from exploration into philosophy. And that possibility is the most unsettling collision of all. But before that future arrives, there's one more layer, a deeper question about why the Higgs mass sits exactly where it does, why the vacuum might be metastable, and whether our universe itself could tunnel into a lower energy state. And that is where the new plan becomes truly insane. Because it may reveal not just how the universe works, but how it ends. And one day, long after the LHC's magnets warm to room temperature and its tunnels sit silent, a new ring may hum beneath the Earth. Or perhaps not. Maybe budgets will falter. Maybe priorities will shift. Maybe physics will pivot to cosmic surveys and quantum simulators instead. But the deeper truth remains. We built a machine to ask the universe what it's made of. And then it refused to say more. So now we build again, not because we are certain of discovery, but because uncertainty is intolerable. You live in a moment where humanity stands, arb, between knowledge and mystery, armed with superconducting magnets and stubborn curiosity. They're turning off the Large Hadron Collider, but what they're really doing is deciding how far we're willing to go to understand why anything exists at all. And that decision might matter more than any particle we ever find. The silence after discovery is louder than the discovery itself. When the Higgs boson appeared in the data in 2012, Confirmed independently by both ATLAS collaboration and CMS collaboration at the Large Hadron Collider, it felt like physics had reached a summit. But summits are deceptive. You think you've reached the top until the clouds clear. Because the Higgs didn't open a door, it closed one. For decades, physicists expected the Higgs discovery to be the beginning of chaos, new particles spilling out, supersymmetric partners emerging, extra dimensions flickering into visibility. Theoretical frameworks had been waiting, almost impatiently, for experimental confirmation. Instead, the universe responded with unsettling restraint. The Higgs was exactly where the Standard Model predicted, its mass, about 125 GeV. Just enough to make the equation self-consistent. But here's where the tension deepens. That number 125 GeV is strange. Quantum mechanics tells us that the Higgs mass should be wildly unstable. Virtual particles constantly flicker in and out of existence, contributing corrections that, mathematically, should push its mass, 18 GeV, where gravity becomes quantum. That's a difference of 17 orders of magnitude. Imagine expecting Mount Everest and finding a pebble. To keep the Higgs so light requires either extreme fine-tuning, the universe balancing, parameters to absurd precision, or a hidden mechanism that cancels those quantum corrections. This is called the hierarchy problem, and it's not a small inconsistency. It's a crack running through the foundation of modern physics. Supersymmetry was supposed to fix it. For every known particle, a heavier partner would stabilize the Higgs through elegant cancellations. Physicists designed detectors to catch those partners. Nothing. Year after year, collision after collision, the detectors at CERN recorded petabytes of data. No superpartners. Just confirmation at this stage became unsettling. Because if the universe is not fine-tuned by symmetry, then perhaps it's fine-tuned by chance. Perhaps we live in one of many universes, a multiverse where constants vary randomly, and only in rare cases does the Higgs mass allow atoms to exist. That idea is controversial. It shifts physics from predictive certainty to statistical inevitability. It says, maybe we observe this universe because we can, not because it had to be this way. The Standard Model has survived every test so far, but survival isn't explanation. Dark matter. It doesn't account for the accelerating expansion of the universe, dark energy. When you zoom out to cosmological scales, the cracks widen. Galaxies rotate too fast. Something unseen is pulling on them. Gravitational lensing reveals mass where no light shines. The cosmic microwave background mapped by missions like Planck spacecraft shows a universe dominated by invisible components. Roughly 5% ordinary matter, 27% dark matter, 68% dark energy, and the LHC has access only to that 5%. So what do you do when your most powerful machine confirms your theory, but your theory explains almost nothing of what's out there? You build something more precise. This is the shift that few people outside physics fully appreciate. Energy was the frontier of the 20th century. Precision is the frontier of the 21st. The next generation of colliders won't just smash particles harder. They will measure the Higgs boson's couplings, how strongly it interacts with other particles, to extraordinary accuracy. Because deviations might be tiny. Maybe new physics doesn't appear as a new particle at all. Maybe it slightly alters probabilities. Imagine flipping a coin predicted to land heads 50% of the time. Now imagine it lands heads 50.1% of the time. You'd need millions of flips to notice. That's what the next collider is built to detect. Subtle statistical tremors. The proposed future circular collider would first operate as an electron-positron collider, a Higgs factory. Producing millions of Higgs bosons in clean collisions. No messy proton debris, just crisp signals. Every decay channel measured. Every branching ratio scrutinized. If the Higgs interacts slightly differently with, say, bottom quarks or tau leptons than predicted, that deviation could hint at new forces lurking just beyond current energy scales. Precision becomes a microscope for the unseen. But there's another layer. The stability of our vacuum. According to current measurements of the Higgs mass and the top quark mass, the universe might not be in a perfectly stable state. It may be metastable. Like a ball resting in a shallow valley, separated by a barrier from a deeper one. Quantum mechanics allows tunneling. Given enough time, perhaps vastly longer than the current age of the universe, a bubble of true vacuum could form and expand at the speed of light, rewriting the laws of physics as it passes. No warning. Everything atoms, stars, chemistry rearranged. The probability is tiny, but not zero. And precise measurements of the Higgs are what determine that fate. Think about that. A machine beneath the Earth measuring particle interactions could refine our understanding of whether reality itself is stable. This is no longer just particle physics. It's existential physics. Yet the deeper you go, the stranger it becomes. Because some physicists argue that colliders are reaching diminishing returns. The energy required to probe significantly higher scales increases exponentially. Superconducting magnets must generate stronger fields. Synchrotron radiation grows more intense. Engineering challenges become planetary in scale. The cost of the future circular collider could rival that of the largest infrastructure projects in human history. So critics ask, is it worth it? Could the same funds accelerate breakthroughs in renewable energy, medicine, artificial intelligence? Why spend billions chasing particles we may never see? The answer isn't simple. Because fundamental physics isn't just about particles. It's about frameworks. Every technological revolution, electricity, semiconductors, GPS emerged from curiosity-driven exploration of fundamental laws. When James Clerk Maxwell unified electricity and magnetism, he wasn't designing smartphones. When Albert Einstein developed general relativity, he wasn't planning satellite navigation. But without those insights, modern civilization would fracture. The risk of not exploring may be greater than the cost of exploration. And yet, there's a philosophical tension emerging inside physics itself. What if the universe is structured in layers, and we've reached the bottom layer accessible to colliders? No new particles, no new forces until energies near the Planck scale, utterly unreachable. That scenario, once dismissed, is gaining attention. It would mean the standard model is not a stepping stone. It's an island, mathematically elegant, cosmologically incomplete, and that possibility forces a deeper question. Is nature obligated to reveal its deepest structure to creatures of our size? Or are we assuming accessibility as a right? The new planet CERN is insane not because it's reckless, but because it's audacious in the face of uncertainty. It says, we will test the Higgs to 0.1% precision. We will map every interaction. We will search for deviations so subtle they hide in the 5th decimal place. And if we find nothing, the silence becomes information. Because even a null result narrows the space of possibilities. But beneath the engineering diagrams and budget debates lies something more human, curiosity bordering on defiance. We refuse to accept that 95% of the universe remains invisible without trying everything within reach. We refuse to surrender to the idea that the standard model is the final word. And yet, as proposals evolve and timelines stretch into the 2040s and beyond, a generational shift is occurring. The physicists who built the LHC are retiring. A new generation is inheriting the question. They must decide whether to invest decades of their lives into a machine that may confirm existing theory with exquisite precision or overturn it entirely. There is no guarantee of revolution, only the possibility. And sometimes possibility is enough. But before this story reaches its quiet philosophical conclusion, there's one more escalation. Because colliders are not the only tools pushing the frontier. Gravitational wave observatories, dark matter detectors buried deep underground, quantum computing experiments probing entanglement at macroscopic scales, they are all converging. And what they may collectively reveal could redefine not just particles, but spacetime itself. The next chapter doesn't ask whether the new collider will work. It asks something more radical. What if the universe is not made of particles at all? For a century, you've been told that reality is built from particles. Tiny points. Bosons, little beads of existence dancing in a quantum field. But what if that picture is wrong? Fundamentally wrong. And proposals for the future circular collider stretch across blueprints and political negotiations. A deeper idea is quietly gaining strength. Particles may not be the foundation. Information might be. For decades, physicists treated spacetime as the stage and particles as the actors. Fields vibrate, particles emerge, forces mediate interactions. Elegant. But when you combine quantum mechanics with gravity, that stage begins to dissolve. General relativity, shaped by Albert Einstein, describes gravity as the curvature of spacetime. Massive objects bend it, objects move along its curves. Quantum mechanics, on the other hand, doesn't care about smooth geometry. It deals in probabilities, uncertainties, fluctuations. When you try to quantize gravity the same way you quantize electromagnetism, infinities explode out of the equations. Uncontrollable. Unphysical. For decades, physicists tried to force gravity into the particle framework. Gravitons. Some approaches are mathematically beautiful. String theory suggests that fundamental entities are not points but tiny vibrating strings, their oscillations giving rise to particles. It naturally includes gravity, but it predicts a landscape of possible universes, perhaps 10,500 variations. Testability becomes elusive, And that's where something radical happens. Instead of asking, what particle mediates gravity, some theorists began asking, what if space-time itself isn't fundamental? Imagine this. You zoom in closer and closer to a point in space, smaller than atoms, smaller than quarks, smaller than anything colliders can probe. At some scale, the concept of distance might lose meaning. Space-time could be emergent like temperature. Temperature feels fundamental. But it isn't. It emerges from the motion of microscopic molecules. You cannot find a single molecule that contains temperature. Likewise, maybe you cannot find a single quantum that contains space. In recent decades, surprising connections between gravity and quantum information have emerged. The mathematics of black holes suggests that the information content of a region of space is proportional not to its volume, but to its surface area. This is the holographic principle. Reality, in some sense, may be encoded on boundaries. That idea, once fringe, is now central in theoretical physics. Even more startling, equations describing quantum entanglement appear to generate geometric relationships. Patterns of entanglement can produce structures resembling curved space-time. In other words, entanglement might weave space itself. If that's true, then smashing particles together at higher energies may not reveal the ultimate layer of reality. Because particles would be secondary, like ripples on a deeper ocean. And this possibility changes everything about the new collider plans. Because the future circular collider isn't just searching for heavier particles, it's testing whether the particle paradigm itself holds. If ultra-precise Higgs measurements show no deviation, if no new symmetries appear, if dark matter remains invisible to accelerators, then the message may be clear. Consider dark matter. For decades, physicists assumed it might be a WIMP, a weakly interacting massive particle. The LHC searched for missing energy signatures that could hint at such particles escaping detectors. Nothing definitive. Underground detectors remain silent. Astronomical surveys see its gravitational pull, but not its composition. What if dark matter isn't a particle in our sector at all? What if it's a manifestation of modified gravity at large scales? Or an emergent phenomenon from quantum information structures we don't yet understand? These ideas are controversial. But so was the Higgs once. The unsettling truth is this: the more precise our measurements become, the more stubbornly ordinary the standard model appears. And that ordinariness is extraordinary, because it forces us to confront a terrifying possibility. We might be living in a universe that is mathematically simple at accessible scales. Not hiding supersymmetric partners. Not concealing dramatic new forces, just quietly following equations we already know. But simplicity at another. Think about water. At your scale, it flows smoothly. At the molecular scale, it's chaotic. At the quantum scale, probabilities smear its behavior. Reality shifts character depending on how you look. Maybe our colliders are probing the wrong layer. And that's where gravity returns to the center of the story. Gravitational wave observatories, ripples in space-time detected from black hole mergers, have opened a new observational window. We are listening to the universe, not just seeing it. Each merger tests general relativity in extreme conditions. Einstein still wins. But these experiments probe the cosmos, not the quantum realm. The grand challenge remains: unify quantum mechanics and gravity. If space-time is emergent from entanglement, then perhaps the ultimate collider isn't circular or linear. It's conceptual. A collider of ideas. This doesn't make machines like the future circular collider irrelevant. It makes them boundary markers. They define the limits of one approach. If deviations appear in Higgs couplings, we gain direction. If new particles emerge, theories sharpen. If nothing appears, the silence becomes a map outlining where not to search. And that map may guide us toward radical reconstructions of reality. But there's another layer to the insanity of the new plan. These machines take decades to design and build. By the time the FCC reaches full operation, entire generations will have passed. Children alive today may be leading the experiments. This is science on civilizational timescales. It demands faith, not blind faith, but intellectual faith, that the pursuit of fundamental knowledge is worth investment beyond immediate return. And here's the paradox. The Large Hadron Collider confirmed the standard model. It validated our deepest equations. Yet that success created the greatest uncertainty in modern physics. Because when your best theory survives every test, the burden of proof shifts. You are no longer searching for validation. You are searching for cracks. The new collider is not built on confidence. It's built on doubt. Doubt that the Higgs mass is accidental. Doubt that dark matter will forever evade detection. Doubt that space-time is fundamental. Doubt that we have reached the bottom. And doubt is powerful. Innovation. It forces humility. As the LHC winds down its current era and transitions toward its high luminosity phase, engineers refine magnets. Politicians debate funding. Theoretical physicists sketch equations describing realities we may never touch. And you exist in this narrow slice of history between confirmation and transformation. One machine proved the mechanism of mass. The next may determine whether our universe is stable, emergent, fine-tuned, or accidental. Or it may confirm nothing new at all. And if that happens, if the FCC runs for decades and reveals only deeper confirmation of the standard model, physics will not die. It will pivot. From particles to principles. From matter to information. From geometry to entanglement. And perhaps, centuries from now, historians will look back at the moment we turned off the Large Hadron Collider not as the end of an era, but as the moment we realized that smashing matter was never the final question. Because the true mystery was never what particles exist. It was why the universe allows existence in the first place. The hum beneath Geneva may fade, but the deeper vibration, the one inside human curiosity, does not. They're turning off the collider, not because the story is over, but because the next chapter of reality may require a different language entirely. And whether that language emerges from a 91-kilometer ring beneath the Earth, or from equations describing entangled bits of information, the gamble remains of the same. We are testing whether the universe is understandable, and that is the most ambitious experiment humanity has ever attempted.